Greetings to you. Welcome to Physics with Ben. In today's video, we want to look at the topic measurements of heat energy. We are making use of this textbook, and this textbook. In our previous videos, we looked at the meaning of heat energy, and we said heat energy is defined as the form of energy that flows from region of high to region of low temperature, which is a result of temperature difference between the two systems. In today's video, we want to look at specific heat capacity, thermal capacity, or heat capacity. So let's begin. Specific heat capacity. The specific heat capacity of a substance is defined as the quantity of heat energy that is required to raise the temperature of the unit mass of that substance by 1 Kelvin or 1 degree Celsius. From the equation, H is equals to MC change in theta. Some textbook we write Q is equals to MC change in theta. They still mean the same thing. So in this video, we want to be consistent with the usage of the symbols. We want to make use of H is equals to MC change in theta. So from this equation, we know that C is equals to H divided by mass times change in temperature. So dimensionally, H is measured in joules, mass is measured in kilogram, and change in temperature is measured in Kelvin or degree Fahrenheit or degree Celsius. So for the sake of this video, we want to make use of Kelvin. So C in this equation is known as the specific heat capacity of the substance. And the units for this guy is joule per kilogram per Kelvin. That is the unit for this guy. We want to look at thermal capacity or heat capacity. Right, thermal capacity or heat capacity. We can represent this with a small c and this with a Cp. The thermal capacity or heat capacity of a substance is defined as the quantity of heat energy that is required to raise the temperature of the entire mass of the body by 1 Kelvin or 1 degree Celsius. So from this equation, we have H is equals to MC change in theta, and this is also equals to Cp change in theta. Is equals to Cp change in theta. So from this equation, if we equate H with this and H with this, we have something like this. We have H is equals to Cp change in theta. So from this equation, if we make Cp the subject of the formula, we have Cp is equals to H divided by change in theta. So we can call this equation number 1. We can call this equation number 2. Call this equation number 2. We can call this equation number 3. We can call this equation number 4. We can still come back here and equate this quantity with this quantity. If we do that, we are going to have something like this. So this implies that MC change in theta is equals to Cp change in theta. And you know that change in temperature is common on both sides, so you can strike this out and then we'll end up with a brand new equation as Cp is equal to Mc. So Cp is equal to Mc. We can call this equation number 5. So the thermal capacity or the heat capacity of the substance is defined as the ratio of energy to what? That of change in temperature. It is defined as the quantity of heat energy that is required to raise the temperature of the entire mass of the body by 1 Kelvin or 1 degree Celsius. So these two equations are the equations, equation 5 and equation 4 and 5 are the equations you use when you want to determine the specific, the thermal capacity of the substance. We want to look at ways of determining the specific heat capacity of the substance. We have methods of determining the specific heat capacity of a substance. There are two ways we can use to determine the specific capacity of the substance. Namely, one, we have the method of mixtures. The method of mixtures. Number two, we have the electrical method. The electrical method. We'll look at them one by one. Let's look at this one. So, method of mixtures. I have set up some stuff here to concretize this method deep in your head. The method of mixtures, I'll clean this and I'll clean them one by one. The method of mixtures makes use of the principle of mixtures. The principle of mixtures state that heat lost by a cold substance is equal to heat gained by a cold substance. Heat lost by a hot substance is equal to heat gained by a cold substance. The method of mixtures makes use of this guy. I will say this before. This is what we call in physics calorimeter. This is a calorimeter. It makes use of the calorimeter. Can you see this? This is what we call the calorimeter in physics. This is how it is built. It is built this way. This is a copper calorimeter. So it is built this way. So I will be explaining how this is done, and this is the lead for the calorimeter. So how is it done? The method of mixtures makes use of the principle of mixtures. The principle of mixtures states that heat lost by a hot substance is equal to heat gained by a cold substance. The substance or the material whose specific heat capacity want to be determined experimentally is first weighed. You can see this. It is first placed on the weighing balance and it is weighed. We call it mass of the substance, mass of the metal. So let's call. So we can say steps in determining the specific heat capacity of a solid metal So first things first, the mass is weighed. The mass of the copper, of the metal, is weighed. That is step one. So we say mass of metal is weighed in kilogram. Second step, the calorimeter without water contents. The calorimeter without water content is weighed. We call it mass of empty calorimeter is weighed. So we write mass of calorimeter, also in kilogram, is weighed. The second step is that you will carry water and pour it inside the calorimeter. So this time around, we say mass of calorimeter plus water will be weighed. Can you see that? So we record that result down. So we say that mass of calorimeter and water, that is MCW. MCW is also weighed in kilogram. Now, from MCW and MC, you can now find the mass of the water. How will you do that? The mass of the calorimeter plus water minus mass of empty calorimeter gives you what? Mass of water in kilogram. Because it is madness for you to carry this water and pour it here that you want to find the mass of the water. It is not done like that. The second thing is that the thermometer is inserted into this guy to record the initial mass. Yes, it is inserted into the calorimeter to measure the initial mass of the water in here. So we write initial temperature of water. Initial temperature of water is measured in degrees Celsius. Now, having done this, the next step is to pour in water into the beaker. Yes. And then gently drop this guy into this place. Yeah. The next thing is you place this guy on the Bunsen burner. And then you heat it up. You will heat this guy and record the highest temperature. Can you see what I'm doing? And record the highest temperature. So we write theta hot in degree Celsius. When the highest temperature is recorded, this guy is quickly removed from here and then quickly transferred into this place. It is quickly transferred into this place. It is quickly transferred here. And then sealed up. It is transferred and sealed up. And then you cover this. The next thing you stir this homogeneously to get uniform distribution of heat energy to this system. Can you see that? And then you record the highest temperature here. We call it theta 2. We call it what? Theta 2. Or let's say theta final. You can call it theta 1, and then call this one theta 2. Also in degrees Celsius. You have succeeded in generating all your table of values or all the data needed to determine the specific heat capacity of this by the method of mixtures. Now, guess what? This guy, the heat is lost from this guy from theta hot down to theta 2 into the calorimeter. Now, The next line of action is to put in the specific heat capacity of water. The specific heat capacity of water is measured, is a constant, and it's given as 4,200 joule per kilogram per Kelvin. That is the value for the specific heat capacity of water. Now, the next thing is specific heat capacity of the metal, which you have to look for. Mind you, have all this information with you. The next thing is to apply the principle of mixtures. The principle of mixtures states that heat lost by a hot substance is equal to heat gained by a cold substance. Now, how do you write that? From the data generated on the board, this is what we have. We write from the principle of mixtures, we write, it implies that heat lost by what? Heat lost by a hot substance is equal to what? Heat gained by a cold substance. Now, this is the principle. We want to customize the principle. How do we do that? We write, in this case, heat lost by this metal, heat lost by metal let's say in cooling, heat lost by this hot metal in cooling from theta hot, the highest temperature recorded when this guy was heated, in cooling from theta hot to what? Theta 2. In cooling from theta hot to theta 2, when it was dropped into the calorimeter and the temperature rises, theta 2 is equal to what? Heat gained by the calorimeter plus water. In heating from theta 1, the initial temperature of the water recorded in the calorimeter, in heating from theta 1 down to what? Theta 2. From what? Theta 1 to what? Theta 2. So this is the principle of mixtures customized. I want you to know that this statement is very, very key in this topic. This statement is very, very key in this topic. We are going to convert this statement into a mathematical equation. So just watch what I will do. So recall that from the equations I wrote here, the quantity of heat energy required to increase the temperature of the unit mass of the substance was given as mass of that substance times specific heat capacity of the substance times change in temperature. Call this equation star. Now, we are going to use this quantity of the equation. So, on the left hand side, we can write that heat loss is equal to what? Heat is equal to H gain, H gain. H loss is equal to what? H gain. Now, heat is gained by calorimeter and the water contents. Now, in this experiment, I forgot something. The specific heat capacity of the calorimeter will also be given. It's also a constant. It's also a constant. It will be given. And then the next thing you have to calculate is what? The specific heat capacity of the metal. So we write, the heat lost by the metal is given as follows. We write, mass of metal times specific heat capacity of metal, that is Cm, times change in temperature. The change in temperature becomes theta hot minus theta 2. So we write that theta hot minus theta 2, that is heat loss by the metal. So equals to, the heat gained by the calorimeter is as follows. We write mass of calorimeter, which is this, times specific heat capacity of calorimeter, which is this, which will be given to you as a constant, into change in temperature. This time is theta 2 minus what? Theta 1 plus heat gained by water, that is mass of water. This will give you mass of water, and everything will be in kilogram. It's equal to mass of water times specific heat capacity of water into what? Theta 2 minus theta 1. At this point, you come back to this equation and you make this guy the subject of the formula. If you do that correctly, this is what you will have. We have Cm is equal to, that is, you divide both sides by mass of the metal times this heat change. Is equals to MC Cc into theta 2 minus theta 1 plus MW Cw into theta 2 minus theta 1, all divided. Let me draw this, let me do this very well. All divided by what? Mass of the metal times change theta hot minus theta 2. With this equation, you can now determine the specific heat capacity of that substance using the method of mixtures. To this, we have come to the end of this particular video. In the next video, I will be teaching us how to determine the specific heat capacity of a substance using the electrical method. Now, we'll also be looking at how we are going to do all the calculations and the latent heat, the change of state, latent heat, of vaporization, of fusion. We'll look at all that and all the calculations. Kindly subscribe to Physics with Ben. I am here to help you guys get your A's in physics. Trust me, a trial will convince you. Click the subscribe button, the notification button, and also share this video to people that need it. See you in the next video. God bless you. Bye-bye.